You mean the low mass gap of black holes?
Oh, sorry. So the slide before this was where you cut off an upper mass, but then there's an even higher mass where you can.
You mean the stars that are
Yeah.
here? The point is, we still don't have the rotating models for these extreme stars. So it's work in progress, because here I used the stellar rotation from Franek code. We would like to have it from Parsec, where we can evolve models in hydrostatic equilibrium with that mass. So stay tuned. Yeah, of course. Anyway, apart from running the actual model, yeah, the shift should be kind of a rigid shift.
Such high
Although
masses,
the winds can.
such high masses, they're mostly convective already, so it's not a
Yeah.
rotation mixed into
Yeah,
this
maybe that is less. So this is a very good point. Okay, so, nature made things even more complicated, because LIGO and Virgo did not just observe a single black hole from a single isolated star, but observed a binary system with an initial orbital separation sufficiently small to make it coalesce within a Hubble time. And there are several scenarios to explain how you can put two black holes so close together. I'm going to discuss only those in which I'm currently doing something, which I'm considering now, which is the isolated binary evolution and the dynamics. The idea of the isolated binary is pretty obvious. Stars tend to form in binaries, especially massive stars. If a binary system can evolve the two stars, become become a binary black hole, then the two black holes may be able to merge. In the dynamical scenario, the two black holes were not related to each other. They do not come from the same binary. They enter the same binary by some dynamical process in an extreme environment. Let's start with the isolated binaries. As I say, this seems pretty obvious because stars form in binaries. On the other hand, the evolution of a closed binary is definitely not something we can model with back of the envelope calculation, because two binaries in a closed binary can exchange mass to each other. They can even enter the same common envelope. Tidal evolution can affect the spins of the two stars. So we need to do some careful calculations. And there are at least two different ways to do this calculation. One is with, let's consider just a few binary systems and let's put as much as physics as we can. Like, let's follow the common envelope with hydro simulation. This is great, but you cannot do it for a large statistical sample because it's computationally challenging. If you are interested in a large statistical sample, then what you want to do is to use some approximation. And this is what we do with the so-called binary population synthesis code. And this is basically what we do in our group. We develop and we use population synthesis code. So currently we have two population synthesis code, MOPSE, Massive Objects in Binary Stellar Evolution. Nicola Giacobo, who's a PhD student in my group, is the main developer of MOPSE. And then the 7 code, Stellar Evolution for Embody, which is developed by several people, and let me mention Mario Spera, who's a Marie Curie Fellow at Northwestern. Why 2 codes? Well, the two of them have very different implementation for stellar evolution. And since these things are quite complicated, then we want to be sure that the main result we get with one code are consistent with what we get with a completely different, almost completely different code. So with this kind of population synthesis code, what we can do is to run hundreds of millions of simulations of binaries just in one day, and to study what are the properties of binary black holes that form out of this system. So this plot shows the total mass, so mass of black hole 1 plus mass of black hole 2, of binary black holes that form out of this very large set of binary simulation. Different lines show different metallicities. The top panel shows shows all binary black holes that form in our simulation. The bottom panel shows only those systems that reach coalescence within a Hubble time, in less than a Hubble time. From this kind of plots, we can immediately see several important features of metallicity. The first one is a confirmation of what we already learned from single stellar evolution, and is that metallicity affects the maximum mass of the black hole. With metal poor stars, we can reach significantly massive black holes. The second very important point is that metallicity affects the efficiency of merge. So then if you consider a coeval stellar population, you evolve it, you count the number of mergers that happen in this population, and you divide this number by the initial mass of the global population, then you get an estimate of the merger efficiency. Well, the merger efficiency for metal poor stars is about 3 orders of magnitude higher than for metal-rich ones. But there is also quite peculiar effect that you can see here by comparing all binary black holes with the merging ones, and is that while we can form binary black holes with total mass up to about 130 solar masses, merging binary black holes can have only a total mass up to 80, 90 solar masses. And this comes from a quite subtle interplay between single stellar evolution and binary evolution. And please keep this in mind for later when we will discuss the impact of dynamics.
It also depends on what is the orbital actual separation of the black holes, right? If you put them actually closer in, what prevents them to merge?
Yeah, this is actually it. I mean, you mean the initial orbital separation of the black hole, or the initial condition, just to be sure which question I should answer?
The initial orbital separation of the black hole.
Of the black
has
holes,
something
yeah,
to do
definitely.
with the initial separation of the star. So if you put
No, it's not the initial separation of the star. The point is that here you have binary black holes that are very far away because they evolved like they were, their progenitors evolved like they were single stars. So they have very large orbital separation, more than 1,000 or 10,000 solar radii, and so they basically evolved as if they were two independent stars, and they can be very massive. In contrast, those black holes that end up merging are the ones that start with smaller orbital separation, that progenitors start with smaller orbital separation, but this means that then they undergo mass transfer, and they undergo common envelope. So their orbit further shrinks, and this means that if they are able to form two black holes, the two black holes are going to merge within a Hubble time. But it also tells us that a lot of the mass of the two stars can be dissipated, can be shed away because of mass loss during dissipative mass transfer and common envelope. So basically this is it, and it's more or less what you say. Yes, Selma?
So in the all black holes, are you assuming that all the hydrogen also collapses into the black hole?
All the, sorry?
Before you said it's not so sure
Yeah.
whether if there's a hydrogen envelope, whether it
Yeah,
also
yeah, these are simulations where the hydrogen envelope that is left collapses to
So
black hole.
that's
It's
probably the
totally
main
right.
difference, right? Because the hydrogen envelope was begun by there's no space for hydrogen envelope for the ones that merge.
Well, yeah, but it's basically what I told you. Well, actually, there is no space for hydrogen envelope in the sense that the hydrogen envelope was removed during Roche lobe and common envelopes. So this is basically what I told you. Yeah. Well, basically what you point at is that if we reduce this with some model for cold collapse supernova that does not allow to preserve the hydrogen envelope, the difference between the two becomes none. And we are pretty sure about that because we have also another version of the code that implements the same prescriptions as Star Trek, for example, which are very aggressive on the luminous blue variable, so they send away all the hydrogen envelope.
Thanks.
You're welcome. So, As I said, nature is always more complicated than we can think about, so there is also another possible, at least another possible formation channel, which is dynamical evolution. When the environment is really dense, higher than about 1,000 stars per parsec cube, then stars and binaries can undergo close encounters with each other, and these close encounters, of course, perturb the orbits of binaries. And you can say, well, this is quite extreme densities, 4 orders of magnitude higher than the density in the solar neighbor, but this is the typical density in star clusters, and we know that massive stars, which are progenitors of compact objects, prefer to form in star clusters and OB associations rather than in the field. And then it's reasonable to expect that some of the black hole progenitors and the black holes itself participate in the dynamics of a star cluster before they are ejected from the star cluster or before the star cluster dissolves into the field. Here I'm considering basically young star clusters, so not specifically globular clusters, which are old and massive, all young star clusters and open clusters. And what are the processes that can affect the formation and the evolution of binary black hole in a star cluster? Well, there are just many processes. I will just mention one, because I don't have time to discuss more, which is a dynamical exchange. So let's consider a binary composed of a black hole and a light star. This binary is not going to become a binary black hole, because the star is, let's say, a solar